Before I start, I would like to thank people. I'm here to present a paper that was started years ago with aspects of a technological nature to assess protease and we've had Professor Marangon, who researched for his PhD in this area, and he supported some of the activities that we've carried out together alongside with other colleagues from the University of Udine, University of Trento, and the Edmund Mach Foundation. I will take the opportunity of the previous speech to also try and bypass some theoretical issues that deal with a very deep problem, a problem that is ever present in wineries, that of protein stability. There's one methodology that is very effective, which is the use of bentonite, and we've just heard that it can be used in a different form. Bentonite acts on the main factors of instability and in a process that consists of several steps, and the first of which is denaturation, or the one that is regarded as being such, the denaturation of proteins which are called thermally unstable, defined as being thermally unstable, and the mechanism goes through aggregation and flocculation. This is a problem that is often associated with financial losses in the winery because of the problem with the product which has already been bottled. So it's important that we stop and prevent the formation of precipitates. Sometimes it's hard to do because sometimes we don't know how to correctly evaluate protein instability and colloidal stability in a system that is very variable and depends on many factors. Things change based on the varietal of the vintage and the conditions, and what we see is a change in conditions. Sorry about speaking so fast. Now, as part of this, the alternative that has historically been used to prevent the problem, which has favored us on many occasions and that allowed us to reach some level of stability, was bentonite. Using bentonite, we all know how it should be used, what it stands for, and the many positives, as well as the few criticalities that it involves, which have already been discussed by my colleagues. And I would add the sensory losses. When we reach protein stability, we feel the differences from a sensorial or sensory point of view. We are food technologists, but not everything has to do with the product itself. We needed to take care not only of protein stability, but also of the sensory aspects. We've worked all the way to just before bottling, and we needed to preserve the sensory characteristics that we've worked so far to preserve. So this solution has been approved by OIV and by the Italian legislation, which resorts to proteases. It's not about adsorption, contrary to the previous solution, but it is based on the ability that certain enzymes have to hydrolyze certain proteins during master processing, trying to attack the proteins that cause instability in wine, the most famous being pure proteins. And within this group, we have macro groups such as chitinases and tomatin-like proteins. Proteases are natural enzymes that can bind very effectively, and it is used in many food technology fields, industries such as meat, beer, and dairy products, because they can hydrolyze our proteins. For years, it was harder to apply it in the winemaking world because of two major limitations. First of all, the pH criticalities. with wine, we work in an acidic pH, and the proteolytic enzymes have found it hard to function well under these conditions. And the second aspect were the inherent characteristics of the unstable proteins in wine that caused the problems that were mentioned by the previous speaker. From this point of view, solutions were found to allow its use for winemaking purposes, and that was based on two macro approaches. First of all, selecting the proteases. The food technologists managed to select proteases that were coming from microorganisms that were active in an acidic environment, such as wine. And the second was trying to make that proteolytic activity and help proteolytic enzymes in their activity through the opening, through the fact of making the site where proteases are active functioning, and that through warming up the fluid. When OIV approved the use of proteases in enology, recommended that must is warmed up, and this is done between 65 and 75 degrees C, and this is functional to the denaturation of the main proteins that are associated with instability, and in particular chitinases with a different denaturation temperature. The OIV also gives other recommendations for this heat treatment, flash pasteurization, namely a very fast pasteurization, and the warming up from room temperature to 70 degrees approximately must happen within a 1 minute period, and that it is immediately cooled down to working temperature. And this is very important because the protease activity happens during this warm-up phase when the proteins open, and that happens very quickly. So that makes it possible not to extend the treatment, especially the heating phase. So certain tests were started in 2019 to see how it worked from a practical standpoint. The first thing that we tried to do was to assess the process in light of a production scale. At laboratory scale, we therefore produced a few test tubes to see if it worked well, using an approach that would just leave the OIV recommendations partially aside and combining the protease treatment with the warming up of the master that led to the production of wines that are stable from a protein perspective at the end of alcoholic fermentation without any additions and without any further treatments. This was very experimental. We then quantified the proteins. We measured the proteins. The data that I'm going to present are based on a number of different varietals to make the test more robust. If the treatment works well, if the enzyme works well, it needs to work well across different varietals. And what we saw was that we reduced the proteins by over 80%, actually over 90%, the PR proteins, and the TLPs. The TLPs even more for certain characteristics that we're going to discuss. This is associated with the denaturation temperature. Chitinases tend to be removed from the medium by alcoholic fermentation as such. TLPs, because of the higher temperature and also the capability that they have to refold, tend to be a bit more resistant to fermentation, to alcoholic fermentation and heat treatment. Within the realm of unstable proteins, it is estimated, and this is a paper that was written a few years back, that tomatin-like proteins above 80 degrees can remain partially, at high proportions, stable in wine. And that's where proteases might become irrelevant. With Marangon, we've started a scale-up experiment in a lab to try and scale up to then industrial scale. We've used very different varietals, Traminer, Gewürztraminer, Sauvignon Blanc, which requires a lot of bentonite for stabilization, and then a few rosés. We've tried to do this while assessing also the effect of heating up the medium, because you may imagine that the most significant event on protein stability is given by heating up the must. But with these three different approaches, we've evaluated the addition of proteases, the heating up with or without proteases. Now the assessment. Okay, just to give you some beef in all of this discussion, we've tried to normalize the data, combining all the data to see if the results that we've seen could be reproduced, so if they were robust. So these are not concentration data, but they have been grouped together and normalized and standardized for statistical purposes. There's a tendency for TLPs and reduction in chitinases due to the presence of proteinases alone. That drives a reduction in must of the chitinases and a tendency to the reduction in the concentration of TLPs. Now, this happens also when we apply the heat treatment, where we further reduce the presence and prevalence of chitinases. But this is a trend that needs to also be compared to practical needs. And the practical needs needed to come to terms with the need for using bentonite in the same wines. So we've measured it against the required amount of bentonite to be used in these wines. The key factor that determines stability is given by heat and heat treatment, the last two columns to the right, but also that there's a tendency to reduce the need of in bentonite. On the right-hand side, you have Traminer data, 100 grams per liter of bentonite as the control group, which reduced and then the procedures that allowed us to reduce the required amount of bentonite. Now, we are in a context where the energy crisis is something we see currently, and where there can be a problem in implementing an end-to-end treatment for wine stability other than heat treatment. So we needed to take an approach in sustainability in our product and an assessment of the organization of the working site and the operational aspects. Let me go back to the characteristics, which is the need for the early test, which is preserving the style of the product and seeing that it is not affected. My colleague will discuss this. But from my point of view, the interest in all of this is to validate it, to see if everything that we have reviewed goes in the same direction and is consistent. When thinking of the previous assessments, the addition of proteases in the must leads to a reduction by 20-25% in the content of TLPs in Gewürztraminer and Sauvignon Blanc, and 65% of chitinases without even needing requiring heating up. So if the theoretical proof works well also in practical terms, if the addition of proteases ends up hydrolyzing the proteins in active sites, releasing peptides, then this is important. So we had to measure the number of peptidic derivatives that are the result of uvic proteins, and the concentration of these products, of these byproducts. The alcoholic fermentation showed that there had been an increase in numbers of the fragments of peptides that come from the grapes and the concentration of these peptides, therefore confirming that even under a heating treatment applied to the must, a reaction and a result are possible. So if heat and protease could give us a complete stability in the must, the addition of proteases without the heat treatment would not always lead to that result. So we took a hands-on approach to see how much we could save. The data you see here are 2024 data. We worked with varietals that are prone to protein instability. And so these are varietals which, from an inherent point of view, intrinsic point of view, have a tendency to protein instability, just like all resistant varietals. And everything was measured in terms of bentonite requirements. At the end of alcoholic fermentation, we could save the amount of bentonite by 30% approximately, but with a variable situation according to the wine of 5 to 7% with at the lowest end of the bentonite saving scale, and 58% at the high end of the scale. But in any case, proteases always helped us save bentonite amounts in the process of attaining protein stability. There can be several reasons accounting for this. We needed to find a pattern now that will allow us to identify where it might be relevant to add proteases, given all the characteristics and all the situations that may vary in a vinification process. Now, this being said, I think time flies, and so I needed to try and be more efficient. One of the goals that we had given ourselves was how to increase the effectiveness of proteases without having to invest in our working methodology, without having to use technologies that are not normally present in wineries. That's where we started working with Professor Cerotti to assess the effectiveness of power ultrasounds onto the protein stability of our wines. I will not delve into the details. This is a very interesting process. Cavitation involves an interesting process, which is a sound cavitation. Sound waves that penetrate into the fluid, they create gas bubbles that cause an implosion. When the implosion happens, a lot of power is released, and because of shearing strength, that will break the cells in the grapes, trying to improve the extraction process, and that can interact with the proteins that are present in the wine. Now, as part of this, there's another process, which is the hotspot theory, which means that during cavitation, temperature and pressure can be very high, over 5,000 degrees Kelvin and 2,000 bars. The consequences of this condition can be, for instance, the formation of radicals, and the radicals, not just because of shearing stresses, they can react with the proteins. So as part of the many papers that were developed revolving around the use of ultrasounds, there are two main categories of protein reactions in the medium. One that leads to degradation, to decay, and Professor Cerotti demonstrated that these conditions can cause an improvement in the protein stability of wine, but under certain conditions, this could lead to an improvement of the enzyme activity. Now, as part of this, and thanks to the collaboration of the University of Padua, and they also provided great proteins to work on, we've studied whether there was a possibility to improve the effectiveness of protease. This is the result where we have compared two different temperatures, two warming temperatures, a natural process which is proposed by OIV with the use of proteases, and we've also assessed how ultrasounds would act with or without proteases during treatment. Oops. You see that in the first two bars, you see the heat treatment compared to the control. We didn't really see degradation effect when it comes to protein decay. And I'm talking about proteins alone, just excluding every other instability factor. In green, you see the ultrasounds, and in blue, you have the combination of proteases and ultrasound, where you see a very clear effect that shows us in the most extreme conditions to a total elimination of tomatin-like proteins in the medium. So we needed to transfer that to the winemaking, real-life winemaking, and so we did this in a wine to assess whether it is possible to obtain the same results in real-life conditions. Now, comparing warming with or without proteases and also the use of ultrasounds in the medium, what we have observed based on the results is that in the first place, the presence of proteases, hot treatment, heat treatment, or without heat treatment will improve or the concentration will reduce the concentration, including that of chitinases. And the increase in the process conditions, the multiplication of process conditions, as was saying before, will improve the effectiveness of the treatment. With chitinases, while keeping the same trend that we've seen for TLPs, we see a prevalence of the heat treatment over everything else. So it tends to prevail over the use of ultrasound, but the proteases would still influence the result positively. Now, if this enzymatic or enzyme activity lends itself to being used under different conditions, then it also needs to be responsive in terms of treatment doses. With an enzyme where the activity is often related to the concentration, the difference is often given by the ultrasound level. Let's not forget that we're talking about wine, and that ultrasounds can degrade proteins and cause, therefore, protein decay. So these are the results we have obtained when you start treating the wine at the highest doses, at the highest level of intensity, with the most energy applied to the system. Then you see a prevalence of the ultrasound effect. But when you do not use a lot of intensity, and so therefore the treatment is softer, the elimination of PR proteins is proportional to the concentration in the enzymes used. So there's a synergy of these two technologies that is proved here, that allows us to also better target this user. I apologize to the translators for having been so fast in my discussion, but I'll now leave the floor to Mrs. Gallo, who will clarify other results, who will present other results of the same investigation. I'm sorry about having to ask you to slow down. Our interpreters are very good, but they are not supermen or superwomen, and therefore, Gianni is saying John is saying you need to slow down to allow them time to translate. Thank you from the translators. Just go get your headsets. I'll try to speak slowly. My slides are in English, although my speech is in Italian. I will continue talking about the proteases.
Stabilizzazione proteica. I will refrain from repeating what previous speakers have said and explained, and I will focus on aromatic implications. The issue, as we all know, is a general problem. Protein stability, especially for white and rosé wines. Several solutions have been put forward, and a recently approved of solution is protease, authorized by OIV. Basically, what the OIV suggests is to add a protease in must and wine, heat 1 minute, 50 degrees or so that the enzyme can act and hydrolyze unstable proteins that derive from the grape itself. Enoforum proposes our protease, which is aspergillopepsin 1, which is in a liquid formulation, and it is an acid protease. Let's now focus possible implications for the aromas. As previously explained, the process entails that you add protease, you heat up to 70 degrees. This is what we did in our test. You keep the temperature for 1 minute, cool down rapidly, and then ferment. At the end of alcoholic fermentation, you have stable wines in terms of proteins. This process can be influenced by three things. So the addition of protease with an action hydrolyzing proteins and releasing peptides, whereby the peptidic and immunoacidic pool can be altered. I changed, therefore, the profile of the available juice for the yeast and its aromatic profile. Then you have heating, which could be perceived possibly as something negative in terms of the aromas, but if performed on the juice, it is not necessarily negative. And then after alcoholic fermentation, you have protein stability, which means that you cut down on the addition of bentonite with all possible consequences. In our tests, we experimented by adding protease with heating and without heating at different temperatures, only heat as well. And here I summarize what we did at the Edmund Mach Foundation in San Michele. I will try and wrap up in a few minutes all these factors. As for the first factor and the hydrolysis of protein, aspergillopepsin 1 decays and degrades proteins and releases peptides. This changes the peptidic profile and also increases the substrate for the exopeptidases of the grapes, which release amino acids. This has an impact on fermentative performances. Indeed, we had a slight acceleration of the kinetics of fermentation, and then there are also aroma implications since I change my initial available must for the yeast. In this part, we analyzed amino acids in the juice, before fermentation after adding protease, and we noticed that in the heat treatment with protease, we had an increase in amino acids, fully in line with what you said earlier on. As for peptides, as previously explained, we did several experiments at different temperatures, including much lower temperatures, including 20 degrees, and we saw that in masts before fermentation, there is a considerable increase in the concentration of peptides deriving from the unstable proteins of grapes at 20 degrees already. So there is an effect of protease even without heating. As for the analysis of aromas on wines at the end of the alcoholic fermentation, well, we performed several tests. Preliminary tests in the lab and semi-industrial tests. In both cases, with reference to the esters, that is mainly fermentative aromas, heating had a major impact, and also heating with protease. So possibly by changing the starting amino acidic profile, the available compounds for yeast entailed an increase in acetates with the treatment. As for terpenes, we noticed both in the preliminary tests and in the industrial tests that it is heating that had a major impact, a negative one in this case. So when treatment was accompanied by heating, there was a higher concentration of free terpenes in the finished wines, while when protease was used without heating, there was no difference. And these tests were performed both on Traminer and Sauvignon Blanc. We then analyzed thiols, varietal thiols. In the lab, we slightly increased the concentration of thiols, while in the industrial tests, we noticed no difference in the treatments without heating and protease. This evidences that despite the fact that treatment can be considered impactful, it is not always so that there are effects changing the profile of the desired wine. Another important aspect that we should consider is that by diminishing or eliminating bentonite, you avoid the negative consequences of having bentonite in terms of aroma, flavor, and mouthfeel. In our tests, we saw that there is a reduction in bentonite even without heating. And this is in line with what Professor Román said earlier on, in that there are several percentages of reduction of bentonite, depending on the variety, depending on the vintage, and the weather conditions. But we always saw that by using only protease, you have a variable percentage of reduction of bentonite. Here you see a number of results coming from wine tastings in Italy. And the sensory profile was not upset or overhauled. You see the volume, especially the wines treated with the protease without bentonite, therefore, were found to be more bodied in the mouth. If you ask about their preference, by comparing controls and the treated wine after 1 year in the bottle, well, enologists preferred the wine treated with protease. Here you have the take-home messages. the protease change the pool of compounds available for yeast fermentation. This has an impact on the fermentation kinetics and also the aromas. There is an impact from heat treatments in terms of a loss of free terpenes, and that is negative. But this derives from heat and not from protease. No difference with reference to volatile thiols. We should also remember that the impact on aromas depend on the variety and also on the winemaking target, in that if you want to have a terpenic wine, it is one thing. Otherwise, you might want to enhance the fermentative or acidic aroma. So depending on that, you will have different outcomes and based on different objectives. When it came to the tasting, oenologists did not perceive a specific impact, if not a different volume in terms of mouth feel. And so by reducing the usage of bentonites, of course, you have less impact in terms of aromas and flavor. There is one point that I would like to insist on, and it is the following. We performed several tests, and initially we used the heat test, and there can be an interference by using a heat test when using the protease, when applying protease. Our suggestion, therefore, is always to make a test with bentonite to actually verify the need for bentonite of the wine after using protease. This is my conclusion. Thank you very much.